We'll start recording now. Once again. Yeah, I'm recording this now. All right. Where do you get the link? I will share the link and I will give you the link to my YouTube channel where you will get to see all the videos. Remind me at the end of the session. I will tell you the link to my channel where you will get to see the recordings. Okay. So yeah, what I was saying is that power electronics, it might sound like that whatever you have studied analog electronics, same thing but in higher power. But it's not actually the same. What I'm saying, not actually the same, is from the point of view that the objective is quite different. It's not only about high power, it's about power conversion. So in analog electronics, you mostly talk about signals, amplification, filtering, and all. But here we'll talk about transformation of power so that we can get whatever level and type of power we require at our end. So the first week mostly covered diodes with Professor Umanand. He talked about two things mostly. One is a switch and the other one is diode. Actually, power electronics is all about these switches. There are three components in electrical engineering which can be considered as lossless. Ideally, those three things are: one is switch, second one is inductor, third one is capacitor. So any power electronic converter will be actually a network. Oh, sorry, I did not notice it, and I've been talking for quite long. Anyway, so what I was saying is that power electronics is different from analog electronics from the point of view that we are not only talking about high power but also talking about power conversion. Okay, in analog electronics we mostly talk about signal, but here we talk about power, not only power conversion. I mean power conversion to a desired level, but also to a desired form. Okay, so the first week of the lecture was about these two components, switch and diode. So what I was saying is that there are mostly three components in electrical engineering which are considered lossless, at least ideally. At least ideally, they can be considered lossless. They are switch, inductor, and capacitor. Okay. So any power electronic converter that you will study throughout throughout the course are actually networks of these three: switch, inductance, and capacitance. You will get to see resistances also, but those are parts of those are load. Okay. A power electronic converter cannot be analyzed or operated under no load because devices are turned on only when you supply some current through them. Okay. So when we talk about switch, there are several types. Diode is also one kind of switch, uncontrolled switch. There are SCRs and there are active switches. Active switches are several types. There are BJT, there are MOSFETs, there are IGBT, there are recently coming ICT, there are GTO, which is quite old. Generally, GTO is not used or used not. So these different kind of switches you will study. But the thing is, when you are studying about the converter, you really do not need to know what kind of switch it is. Uh, the scene is a bit different for diode and thyristor, means SCRs, where you need to know a bit about them. But for the others, especially the active switches, you need not know about the characteristics. All you need to know is that when they are on, the resistance is zero, and when they are off, the resistance is infinite. No current is flowing through it. That's all. That's all you need. At least for the fundamental course of power electronics, first one or two courses, you need not know much about the switch characteristic. So that's about the introductions. I can see some hands raised. Do you have some questions? Alright, so I will start not for this class only, for every class I will start with doubts from you. So I hope you have already watched the videos, and if you have any doubts I will try to answer them, and then we will go for some questions which will be closely related to the assignment questions that you will get this year also. Yeah, doubts from you. No doubt? Okay. Transistor. Okay, go ahead. All the transistors are covered this week. Yeah, what's your doubt? Uh, we are not covering the current assignments here, and also this is the first week, so we'll be covering only the week one materials today. Yeah. Yeah. Okay. Manoj, please mute yourself. The Tatra is going to ask something, but he left the meeting. I think network issue. Yeah, the Tatra. Yeah. Actually, once again, I cannot discuss the assignment questions directly here because you are supposed to do them since your certificate and scores directly depend on them. But okay, anyway, I will discuss something of the dive how to put search. Actually, let me generalize. Okay, okay. So I will have a general discussion about switching method, okay, switching process, how it goes. So the thing is, suppose you have this VIP, okay, this voltage, this is correct. Now, when a switch is off, when we say off, we mean open. So when a switch is open, where does the operating point lie? The operating point lies somewhere here. The current is zero, but there is some voltage which the switch is blocking. Again, so this is open. When the switch is closed, means on, it is lying somewhere here. Some current is flowing, ideally speaking, zero voltage across the switch. But the question is, what about the transition? See, the transition can happen in several ways, but there are two ideal ways of transition. One way is, say I am talking about turning on process, okay? Turning on process, right? So it was turned off means open at this process, at this point. So it is turning on. So what it does is, in ideal situation, the voltage first becomes zero, then the current rises. Okay. So if we look at the voltage and current plots, so this was a large voltage and a large voltage and zero current. Zero current. The voltage first comes to zero. then only the current rises like this. So this is one ideal situation. Why is it ideal situation? Because if you see, the instantaneous power lost across the switch is always zero throughout. So now the power lost across the switch during the steady state, that is when it is steadily on or steadily off, is anyway very close to zero. But during the transition, what we call is the switching period, at that time also in this case the power lost is zero instantaneously. Once again, while turning off, this might happen that current first comes to zero, then the voltage rises. That is, current first comes to zero, then the voltage rises. In this case also, the power lost across the switch is zero. So basically, this is the ideal switching process, but this does not happen. This we sometimes also call rectangular switching. In reality, something like this might happen. Okay, uh, so neither the voltage comes to zero first or the current rises later. Both of them happen almost together. So you have a non-zero loss. So in case of diode, what happens? Actually, there was a lecture also. Professor Ramanand had this lecture that you have this voltage, you have this load. If I call this V, and if V suddenly becomes negative, say this was 0, say this was some plus 10 volt, so minus 10. If V suddenly becomes minus 10 volt, what would happen? So if this is the diode current, this is the diode voltage. Initially there was some positive current, okay, and zero voltage across the diode. At this point, V becomes negative. So what happens is, diode is a semiconductor device. It's not a mechanical device that will suddenly turn off and stop the current. It will take time. Okay. So as soon as the V becomes negative, diode is still on. So the negative voltage will try to push a negative current through the resistance. So the current through the diode will suddenly come like this. I am drawing this across time. Okay. And then this will decay, then this will decay and become zero. Voltage probability rises from somewhere here, like this. So basically what you have here, you have some negative current flowing to the diode. What happens to this current? See, you have some area here, right, under this curve. So if you do an integration of this, or you find out the area equation of IDT, what you get is charge. This charge is called the reverse recovery charge. So the diode in its depletion region got some charge stored, which kept the diode on. Now, when you are turning off the diode, those charges are to be removed. Then only the diode is turned off. So this is the time that the diode takes to turn off, the reverse recovery time. So not this actually, from here it starts, the removal starts from here. So whatever time it takes, that into voltage will more or less give you the loss. In the question, is there any how many switching actions are there? Rectangular switching is the ideal case. Rest depends on, actually, if you study about MOSFETs and all, there is one very standard switching process. Uh, I don't know whether it will be covered in this course, but there is mostly one we talk about. So it's not that how many types are there. MOSFET is a device and it shows its characteristic. Diode is a device, it shows its own characteristic. Rectangular name was given to the ideal switching process. That generally doesn't happen in semiconductor switches at least. In mechanical switches that might happen. Mechanical switches you can say rectangular switching more or less. But still we can sometimes also see the discharge in mechanical switches also. So okay, could I answer your question? That's okay. A diode part number is mentioned in the question. We have been asked to find out conduction loss. Conduction loss in what? Hmm, hmm, hmm. Actually, I cannot discuss current year's assignment. At least until you submit them. Mhm. No, I don't think I can answer it right now, but after you submit it, I can. We'll see next week maybe. Yeah, right now I can discuss. Okay, can someone tell me why do we not use mechanical switches in power electronic converters? Why do we have to use semiconductor switches? Mechanical switch is better, no? Almost zero conduction loss. In any case, we are not first because electrical circuits they have time period in the range of millisecond, right? So we have to have switching also in that range only. So maybe the minimum switching frequency that we start with is maybe 5 kilohertz. There is a minimum, a very low frequency. 5,000 times a second you are turning on and off a switch, and electrical engineers call it very low frequency. So that doing that with mechanical switch is not possible. Even using machines, it's not possible to do. So that's why that is not used. And 5 kilohertz, as I told you, very low frequency up to about gigahertz. Okay, so yeah, any more doubt? Yes, I am recording this session and I will upload this on my YouTube channel. I will send you my YouTube channel link. Yes, that has been recorded. I will send you just a second. First, I am sending you the last day's recording. Now I will send you my channel link. Yeah. I am not sure what they are planning to do this time, but last year in the channel, in the course announcement section, the channels were mentioned, and also the Google Sheet was shared with the students, where we keep uploading the channel links and everything. Yeah, so the channel that I have given you, that is my channel. You will get all my videos there. All the say my sessions recording will get there, and the other one I have sent for the last days. In that channel also you can subscribe and you can get other days recordings. Okay. And first of all, we are not professors; we are PhD scholars, and this Monday session I will always take. Every Monday I will take this session. Yes, and Mr. Chitendra Kumar will take a Tuesday session. Alright. So, any more doubt, technical questions now? Any more doubt? Okay, then I will discuss these questions. Yeah. Junction capacitance about MOSFETs. Junction capacitance, I'm not really sure about. Actually, see, if this is the P and N zones of um, the diode, we have some metallic contact here and the nodes. This is the depletion region, right? And you have charge accumulations here. Probably negative on P sides and positive on N side. Some depletion region you have. So basically, you have a kind of voltage difference here, kind of potential difference. What is the polarity? Do you remember? Is it like this? Just a bit. See if I put it actually, it will go like this. Yeah. So basically, you have charge accumulation on both sides of something that can be anything. That need not be a metallic plate, but some non-conducting material in between, and you have charge accumulation. So this basically creates kind of capacitance in between. So since you are asking questions about devices, let me tell you one thing. There are some people who are taking polytechnic course for the first time also. For the first one or two courses in power electronics, you really need not bothered about the devices. Okay, so because you will study many things. Say you will study DC-DC converters, you will study DC-AC converters, you will study AC DC converters. AC converters are not that popular now, as far as I know. AC whenever we need, we do it AC DC AC. That gives better controllability at output. So all the kind of converters that you will study, you will get to see mostly three kind of electronic devices. One is diode, other one is thyristor, and the third one that you will get to see, most of the times we will not even draw a MOSFET. We will not even draw an IGBT. We will simply draw a switch like this. Because when you are studying this kind of converters, you need not know what kind of active switch it is. Just think about it like an ideal switch. When you close it, zero voltage across it, infinite current through it. When you open it, zero current through it, and it can withstand infinite voltage. Just think about it, think like that. Then you go for analyzing the circuit. Once you are going for actually making the circuit, actually designing the circuit, then you have to come to the device characteristic. But still, device characteristic is still far away. First, you have to know the voltage and current rating of the devices. Once you know the voltage and current of the devices by circuit simulation, not simulation, by circuit analysis, then you can choose the device, which device you need, some part number of MOSFET and whatever you need. You can find it. Then you have to make a gate driver. Do you have a basic idea of how a power converter looks? Okay, let me discuss this first instead of devices. I don't know about others, but the power electronics engineers, mostly who I have seen, are generally not very much bothered about devices, at least in this level. So it's about you have some power source one. Okay, what it is, say, let us say it is your household power source, 230 volt, say 1 kilowatt, single phase. Okay, now you have one induction motor. This induction motor is also 1 kilowatt induction motor, but it is three phase, say 60 hertz. Okay, your household supply is 50 hertz. So you have some power. You have 1 kilowatt supply here, and all you need is 1 kilowatt, but you cannot directly connect it because the levels are very different. This is say 100 volt three phase induction, 110 volt. You have bought this induction motor from US and using it in India. Okay. Now this thing cannot directly connect to the motor. So what you need? You need a power electronic converter, PEC. This will come to this converter, and this will then supply the inverter. What will this converter do? This will convert this single phase AC to three phase AC of required voltage level and frequency. And there will be something to run this power electronic converter. One of them is control. Okay, and other this control actually feeds. You cannot directly connect the control to the power electronic converter. So the circuitry that talks to the power converter is actually gate driver, GD. Gate driver. What is a gate driver? When you are turning on an active switch or a semi-active switch like a thyristor, you have to supply some current to this. Then only it will turn on. Not only that, isolation is another requirement, but I will not discuss isolation today. So this gate driver will do that. The controller will ask the gate driver to turn on a certain switch. The gate driver will turn on that certain switch. In that way. So what I was talking about is when you are going to design this gate driver, not even the modern gate drivers, the regular gate driver when you are going to design, then only you have to go very deep into this device, like the junction capacitances. If you talk about MOSFET, there are, see, this is a MOSFET. If this is a MOSFET, then there are three capacitances like this. Then you need to know about all of them, about their values, about their characteristics, about how to charge them, how to discharge them. So these things comes quite late. At your level, what you must concentrate on is how the circuits work. At the end of this course, you must have the confidence to, you know, must have the confidence that whatever circuit might be given to you, you should be able to derive the output voltage expression of it at steady state. So is it clear what I'm trying to say? Why you need not think much about devices? As of now, just think it as on and off. On and off. Whatever device is being covered in this course and whatever materials are being covered, that you study. But for the first few courses, at least what I feel, you need not know much about devices. Thyristor you have to know a bit because it is kind of weird characteristic. Otherwise, active switches you need not know much. Okay, so the why I was telling all these things about these capacitances. So this charts probably what this capacitor stores, and you have to discharge it through keyboard. Okay. Yeah. Anything else? So I will discuss this problem. See, the thing is, since if some of you have already attended last class, maybe last Friday's class, probably you have seen some of these problems. But the thing is that um, making 6 hours of materials from a 2 hour of lecture is probably not possible. So I will discuss these things once again. If you think, if you still have some doubts, you want to ask something, you can ask once again. No problem with that. So what we're talking about is switch. So three things we will keep saying in power electronic circuits. One is switch, another one is inductor, other one is capacitor. Okay. So first thing is switch. Which one is the of the following is true for an on state of an ideal switch? We just discussed that current can be of any value and the voltage is zero because it's short circuit. On state means it is short circuit. So the voltage is zero and the current can be of any value. Any doubt about it? I don't think there is. Okay, let us try to add some value to this question. If this is an ideal switch, what do you think? Okay, how it came, sir? So an ideal a switch, what I am drawing are say copper leads made of copper, like this. So they are open, physically open. Current cannot flow through it. And when I am closing this, it is touching. Again, it's made of copper. So when it's touching, there is no resistance. Any amount of current can flow through it. This ideal switch, any amount of current can flow through it in both the directions. And when it's open, it can withstand any amount of voltage in both the directions. So basically an ideal switch is a 4 quadrant switch. You know about quadrant of switches? Quadrant of switches. So this is current and this is voltage. An ideal switch can an ideal switch can operate in all 4 quadrants. It can carry current in both directions. It can withstand voltage in both directions. So it is a 4 quadrant switch. It is working in all four. It can work in all 4 quadrants. We will talk about quadrants of switches maybe. There is one question we can. So what I was going to discuss here is if this is an ideal switch, can we say what might be the equivalent circuit of a practical switch? This is ideal switch. Say if we think about mechanical switch when you turn it off, it really like off. Like there's no way that even leakage current can flow because there is a physical large separation. But since we are talking about power electronics, there is the semiconductor switches. They are actually not physically separated. There are ways for the current to flow. So even when the current, even when you are turning off a semiconductor switch, if there is a voltage, it's obvious there will be voltage. If you're turning off a switch, that means it is blocking some voltage. This voltage will try to push some current through the opening. So we can draw it in a better way. A very high resistance parallel to the switch. So if this resistance is say R off, if I say, then the leakage current flowing through the switch is the voltage VB that the switch is blocking given by the R off. that much leakage current is flowing even if you are turning off the switch. And while you are turning on the switch, there is some conduction loss. So that can be represented as a small resistance. So if R off is in the say level of mega ohms, R on is in the level of milliohms. In this way you can think about. So this you can say the equivalent circuit of a practical switch. But again, when you are studying at least for this course and maybe one more course of power electronics, we will mostly talk about ideal switches, not this kind of switches. In fact, circuit analysis when we do, not think about this kind of non-ideal. These things come later. So some messages came here. Any doubt about it? Now we get to see some uh, real devices. This kind of device is used in some cases. So a power electronic switch is realized by connecting a power MOSFET with body diode. This thing is called the body diode of a power MOSFET. This diode is not separately connected to the MOSFET. If you study the inside the construction, the semiconductor materials are there put there. This diode is somehow gets created in the MOSFET, and it can really conduct current in this direction. So with a body diode in series with a power diode. So this is a MOSFET. This whole thing is a MOSFET, and it is in series with a power diode put in this fashion. Identify the static operating points on the VI plane. So the VI plane we were talking about just now. Say if this is I, this is V. So when we are asked to identify the static operating point in the VI plane, you have to think about two things. In how many directions it can block the voltage when it is turned off. In how many directions it can carry the current when it is turned on. Okay. Now suppose I have turned off the device, means I have not given any gate signal to the MOSFET. Okay. I have not given gate signal to the MOSFET. Now let us see whether, okay, one more thing is you have to define a, you have to define a assumed positive direction of voltage and current, right? So I am taking this direction of voltage as my assumed positive direction of voltage. I am taking this direction of current as my assumed positive direction of current. Okay. I am not actually applying this voltage polarity. These are my assumed positive direction of voltage. You will understand it better in system. Now my switch is off. I am not giving it power. Now I am giving a real voltage of this polarity, a real voltage. Can this voltage make any current flow through this device? It cannot. Because you see, this body diode will stop the current. This body diode will stop the current to flow. So, this device has a capability of stopping a voltage in this direction. Now, see, this voltage direction is same as my assumed positive direction of voltage. So, I can say this device can stop a positive voltage. Right? Unless I define this as assumed positive direction, you cannot say whether it is a positive voltage or it is a negative voltage. So it can stop the positive voltage. Can it stop negative voltage? Can it stop negative voltage? It can stop negative voltage because this guy will stop the current. It can stop negative voltage. So it can stop negative voltage also. Okay. Voltage waves is what about current? Now we have to find out in how many directions it can support current. So to understand that, we have now turned on the switch. The switch is now on. Okay. Current can flow like this through the switch, then through the power tile. So this direction is coinciding with our assumed positive direction of current. So this is possible. Current cannot flow like this. This diode will stop the current flow like this. So this is the operating region of the switch. This is the operating region of the switch. It's a two-quadrant switch. It is operating in quadrants 1 and 2. A diode is a one quadrant switch. You can operate only on the first quadrant. There are several ways in power electronics where we can even realize four quadrant switches using MOSFET and diode combinations. Four quadrant switch means just like a mechanical switch. You can stop voltage of any direction. You can stop you can supply or carry current in any direction. Like this switch can stop voltage in two directions only, but can carry current in only one direction. Right? Yeah. Not the body diode alone. When you are talking about this switch, we are talking about these two terminals. This whole thing makes a switch. This and this is possible, isn't it? It can stop negative voltage and positive current. Stop negative voltage. It can support positive current. So second quadrant is possible. Yes. Yes. When you are talking about stopping the voltage, you have to not assume, you have to consider the case that is it's already off. Yes. Yes. No, no. See, those two are not happening simultaneously. If the switch has capability of for positive current and positive voltage, that means it is operating in first. It can operate in first quadrant. We say it's a first quadrant switch. In this case, it can have capability of both first and second. Yes, but not simultaneously. It can stop a negative voltage. For example, a diode, it can stop a voltage only in one direction, in this direction only, and it can carry a current only in this direction. So it's a single quadrant switch. For example, if you talk about MOSFET, so only MOSFET, there is no such series diodes like this. This MOSFET, see, this MOSFET cannot stop a voltage like this, can it? Because there is a body diode. Think about this MOSFET only. There is no diode connected in series. Only this MOSFET. Can it stop a voltage like this? It cannot, because the body diode will flow, will conduct. So a MOSFET only, it can stop voltage in one direction, in this direction only, and it can conduct current in both the directions. So If you talk about a MOSFET only, you can say it's like this. If I talk about just a MOSFET, it can carry currents in both directions, but voltage in only one direction. You can stop voltage in only one direction. Uh, I cannot hear you. You can write in the chat box. Okay. Flow the current or stop the voltage. Okay, since we are talking about this, let me give you an example. You can just keep a note of it. The switch looks like this. See, suppose I have one active switch. Like this. Suppose I have one active switch like this, and to the active switch I connect four diodes like this. Can you tell me how many quadrants would this combination work? See, this whole thing is a switch now, okay? And the terminals are A and B. All the four quadrants it will work. So this is very much like a mechanical switch. It can stop voltage in all directions. It can allow current in all directions. All direction means both the directions it can allow current, both the directions it can stop the voltage. There is another way of realizing this thing, which is like this. This combination also is a four quadrant switch. It can allow current in both directions. It can block the voltage in both directions. This is also four quadrant switch. But the problem, okay, can you tell me what is the advantage of the first one compared to the second one? Or maybe which one is more advantageous? What do you think? Both have their own advantages. So this someone's going to this one is polarity relation is true and Lalita, are you seeing any polarity reversal too? I'm not seeing any polarity reversal. It's not that polarity wise they are very sensitive. When you get a MOSFET, there is a data sheet. A voltage is mentioned there 400 volt MOSFET, 600 volt MOSFET. Once you are not exceeding that voltage, you are safe. As long as you are not exceeding that voltage, you are safe. Yeah, any idea which one is, or maybe what are their pros and cons? Okay, I will try to see their working. Okay, so suppose You have turned this, I am talking about the case one, you have turned this switch on and current is flowing like this. So there was a voltage like this which is making current to flow like this. So current is flowing like this. In this case, say you turn this on, current is flowing like this, right? So in the first case, current is flowing through three devices, whereas in the second case, current is flowing through two devices only. So your conduction loss is more in this case. Conduction loss is more in this case. Not only that, your device count is also more in this case. There are five devices here, there are four devices. But when I'm saying your device count is more, can you say that device count is more means cost is also more? Actually, no. Why not? Because in the second case, if you see, active switch is more. In the first case, there is only active switch. Second case, there are two active switches. So when you are having a lot of active switches, keep in mind you have to give gate pulse to all the switches. In the first case, we had diodes. Diodes you put in the circuit that will work according to the polarity. But when you have active switches, you have to not only provide gate pulses to them. Gate pulse will see there are a lot of things. There will be a gate driver, there will be an isolation, there will be a isolated power supply for the gate driver, so many things. At the same time, you have to, I mean, your algorithm is also changing in the microcontroller wherever you are writing to control the converter. There also you are now writing code for two switches. For the first case, your code was only for one switch. So whole complexity increases with the number of active switches. Okay, so footprint wise, second one might be smaller, but cost wise it might come out that overall footprint wise also, second one is much more expensive. So if you ask me, I will use the first one. Easier to control, lesser headache. Gate driver is a headache. Headache means do not get afraid about it. I'm just saying, like you have to have isolated power supply and all. If we ever later on maybe when we'll talk DC converter, remind me I will talk about isolation. We have to do the isolation. Okay, so switch quadrants are understood. You just can keep note of these two combinations. They are very popularly used for quadrant switches. Okay, so I will go to the next question. The following figure shows the transition of a switch. Find the peak instantaneous power loss in watts. Consider turn-on transition time 5 microsecond and total switching period 50 microsecond. So how to do this problem? Don't you think that it would be maximum here? Somewhere here. So they start at the same point, they stop at the same point. So maybe 50 volt times 5 ampere to 50 watt. That is the peak instantaneous power. Okay, let us try to solve this. I think it will be answer. So what is the equation for current? Hmm, yes. So 10 by T1 times T, right? What is the instantaneous, what is the equation for voltage? is 100 minus 100 by Tn times T, right? So what is the equation for power? This times this. So you have some 1000 by T1 times T minus 1000. What is the by T1 square T square, is it? Tell me if I'm wrong, okay? So if you now do dp dt, dp dt equals 0 and b. So we get 1000 by T1 equals 2000 T by T1 squared. So basically what we are getting is T1 is 0. So T is T1 by 2. So T1 by 2 at the middle of the switching period, we are having the maximum power loss. So since they are linear, current is half, voltage is half, 50 into 5, 250 watt is the answer. Since we have done this far, suppose in this question you are asked what is the switching loss of this switch. Since we are talking about only the turn on situation, we have no data about the turn off. Say you were asked about what is the turn on power loss of the switch. How will you do that? Can someone tell me? You have been asked to find out for this switch what is the turn on power loss. You are not being asked about the peak instantaneous. You have been asked to find out the turn on power loss. How will you do that? See, you have the expression for power. You have the expression for power. The thing is, every time, say this switch is there in some circuit, okay, and the circuit is operating, means the switch is continuously turning on, turning off, turning on, turning off. Every time it is turning on, it is seeing this kind of phenomenon through it. So this kind of power loss through it, right? So how much energy is lost in one cycle? That is integration over p dt. This is the energy, switching energy lost in one cycle, in one switching cycle. Right? Now the total power loss is, so this much energy is being dissipated every cycle. Power loss is energy per unit time, means energy per second. So how much energy is lost in 1 second? This energy is lost in one cycle. So if I multiply this energy loss with the frequency f, means number of times a cycle is happening in a second, that will give me the power loss. So basically, frequency times, if I draw this area, say this is the power loss area, power loss. So frequency times the area under this curve will give you the power loss. Switching power loss. In this case, turn on power loss. We don't have the turn on data. Now see here one thing. Keep this in mind. Never forget when you are studying power electronics. You see, say the same circuit under the same voltage and current, this current conditions, when we are operating, this much power loss will happen, right? This much power loss will happen. Now the total power loss is proportional to the frequency. So if I increase the frequency, if I increase the frequency twice, the power loss will become twice. I am keeping the voltage level same, I am keeping the current level same. Only thing is I am turning on the switch faster. Turning off the switch faster. Say previously it was 10 kilohertz, now it is 20 kilohertz. So your power loss will be twice. So keep this in mind. Switching power loss is proportional to frequency. Increasing frequency has a lot of advantages in power electronic converters. So in we will study DC converter, I will discuss why we need or why we want high frequency. High frequency makes your circuit small. High frequency makes your circuit small. Say for example, the nowadays very high power adapters are coming for your mobile fast charging, 30 or 25 volt, very small converters. That is being possible because they are going for very high frequency, but that comes with a cost. That comes with the cost of what? Comes with the cost of this loss. There is another problem, other problems also like EMI and all, but this is the biggest problem, loss. Because loss is proportional to frequency. Because if you increase the frequency from say 10,000 to 12, say to 20,000, previously this thing was happening 10,000 times a second. Now it is happening 20,000 times a second. So the same power, it is now dissipating twice a second. This your power loss is more. So high frequency circuits have their advantages, but it comes with the cost of loss. Okay, keep this in mind. Power loss, switching power loss is proportional to frequency. Okay, so any question about it? What is cheaper? No, they are not cheaper. They are not cheaper. But actually, I told you, na, there are three things: inductor, capacitor, and switches. If you go for high frequency circuits, your inductor and capacitor requirements reduces. Say in a low frequency circuit, if you need 1 millihenry inductor, say at 10 kilohertz, maybe you need 1 millihenry inductor. At 20 kilohertz, you will require half millihenry inductor. So the inductor size will now become small. So your circuit footprint will become small. Your circuit weight will reduce. But that I will show that I cannot show you right away. When we'll study about DC-DC converters, maybe from 6th or 7th weeks, there I will show. There are direct expressions. From the expression itself, you can see. If you increase the frequency, your required inductance will reduce, your required capacitance will reduce. But right away, I cannot discuss those things. That will divert us from what we are talking about. And the very first class of DC-DC converter, I will discuss about it. Okay, so power loss, why it happens and why it increases with frequency, these things are understood. Okay. This thing is kind of a very interesting problem. Not necessarily a power electronics problem, you can talk about another things problem also. So two diodes are there, D1, D2. So maybe their semiconductor material is different, or maybe they have some other property. But what the problem is, this D1, it has a cut-in voltage of 0.3 volt or forward drop voltage, and D2 has 0.7 volt. So when D1 is completely turned on and conducting, the drop across it is 0.3 volt. For D2, it is 0.7 volt. Okay. Question is, what is the current flowing through the circuit? I is how much? Right. Now, if D1 and D2 were identical diodes, we could have easily said that both of them are conducting. But they are not identical diodes. So we have to find out what is the situation there. Right? So as of now, what we can do is we can start with assumption. What we can assume? We can assume that both the diodes are conducting. Okay. Current value we do not know, we need not know, but both of them are conducting. So if both of them are conducting, the voltage here is 0.3 volt and the voltage here is 0.7 volt. But that cannot be possible because they are in parallel. They are in parallel. So both of them must have the same voltage drop across them. So both of them cannot be conducting together, right? So maybe we have several situations. Say 0, 0, 0, 1, 1, 0, 1, 1. 1 means conducting, 0 means not conducting. So 1, 1 is not possible. 0, 0 is also not possible. At least 1 will definitely conduct because there is a voltage. Okay. So let us talk about this. Whether it is possible that D1 is not conducting but D2 is conducting. So D2 is conducting and D1 is not conducting. So this is D1 is not conducting, D2 is conducting. So D2 has a 0.7 volt drop across it. Right? Since D2 is conducting, 0.7 volt directly comes from its characteristic. Now since they are in parallel, D1 must also have 0.7 volt drop across it. But the thing is, in case of D1, the cut-in voltage is 0.3 volt. So if you are forcing 0.7 volt across D1, it must get turned on. So even if D2 gets turned on for some reason, D1 cannot remain turned off. D1 will be turned on. So this is also not possible. So D1 now gets turned on. 0.3 volt. So D1 is conducting. Now what is the voltage across D2? So it's the same voltage coming across it. 0.3 volt. For D2, the cut-in voltage is 0.7 volt. But it is now getting 0.3 volt only, so it is not yet forward biased. So it is off. See, this situation is a steady state situation. It can stay like this. It can stay like this. So definitely, what will happen in this case is the diode with smaller forward voltage drop will conduct. D1 will conduct, D2 will not conduct. The question is how much is the current? Now we can find out the current. 5 minus 0.3. Whatever it comes that much ampere. Is it clear why you want D1 conduct and not D2? Yeah, probably there was such a question in Nationals ki Boyle's Tech Nationals ki, I don't remember. That is not a power electronics book. That is analog electronics book. It was there probably. Anyway, since we have talked about this, let us talk about another situation. Suppose you have, say, 3 diodes. Ah, let us not take 3 diodes. 2 diodes. 2 identical diodes. And there is a load like this. Okay. They are identical diodes, but different amount of voltage is impressed. This is called a common cathode configuration. Cathodes are shorted, common cathode configuration. Can you tell me which diode will conduct? Let us say both will conduct. Okay, they are identical diodes and ideal diodes. Okay, so if both are conducting, ideal diodes means when they are on, voltage across them is 0, right? So this diode would want 10 volt here, this diode would want 5 volt here. So if both of them are conducting, this same point has to be at 10 volt and 5 volt at the same time, which is not possible. So both diodes cannot conduct. I have got one answer, that first one, we will see. Let us say the second diode is conducting. Let us say the second diode is, means this lower diode is conducting. Okay, this one is not conducting, the upper one is not conducting. The lower diode is conducting. Then this point is at 5 volt. So if this is at 5 volt, what about the upper diode? This is forward biased. So who is stopping the upper diode to conduct? So it will also start conduct. So only the lower one cannot conduct. Now the upper one starts conducting. Now once the upper one starts conducting, the voltage here becomes 10 volt. Now the lower diode becomes reverse biased. It stops. So only the upper diode will conduct. You can see if you have multiple such diodes, then also the diode with highest anode voltage will conduct. So keep this in mind. If you have multiple diodes in common cathode configuration, then the diode with highest anode voltage will conduct. If you have several diodes with common cathode configuration, then the diode with highest anode voltage will conduct. Similarly, if you have multiple diodes with common anode configuration, means it is the opposite. Yes, lowest, not knee voltage, cathode. Lowest cathode, the diode with lowest cathode voltage will conduct. These two things you write in your copy and keep a note when you will study single phase, not single phase, say 3-phase rectifiers and all. There will be 3-phase supplies and all. 3 diodes will be competing. Which one will conduct? So there you have to find out in which configuration are they. Which one is having the highest anode voltage, that one will conduct. In 3-phase rectifiers, controlled and uncontrolled rectifiers, this concept will come. We will record this. Okay. From the piecewise linear characteristic of the diode given. Okay, any question about this? Alright. From the piecewise linear characteristic of the diode given, the load resistance should be how much for maximum power transfer from the source to load? See, the source itself doesn't have any resistance. This thing has some resistance. RS is given 3 ohm. So you can understand, right? We have to find out the diodes are on, and whatever R1 plus 3, that will be RL for maximum power transfer. How to find R1? It is very easy here. Why is it easy here? Because if you look at the IV characteristic of the diode, it is a straight line, right? So in whatever point you might operate, the slope is the same, right? So the resistance is same. The resistance is not a function of the operating point of the diode, right? Find out the resistance. What is resistance? V by I, or I can say del V by del V, right? So what is del V? From here, take this point. So 0.5 to 0.8, 0.3, and by 0.9. So 1/3, right? So 3 plus 1/3, so 10 by 3. This is the total source resistance. So if I have this equals RL, I will have the maximum power transfer to the load resistance. Is it clear? So if I have RL equals 10 by 3 ohm, I will have the maximum power transfer. Then the question is maximum power transfer from the source to load is how much? You can find it, right? Power is V squared by R. So 100, not 100. So if you have 10 volt at maximum power transfer, you have 5 volt drop here, 5 volt drop here, right? Because they are same. So what is the maximum power? 25 squared by R. 2.25, isn't it? Pmax. Conduction loss of the diode is the same. I squared R. Clear? Okay. Space for this question. A 10 volt RMS 50 Hz source is connected to a resistive load of 150 watt for half wave rectifier. Find the value of the theta in degrees such that. Achha. So basically this talks about the cut-in voltage of the diode. You have the sine wave like this until your sine wave, the supply voltage crosses zero point 0.7 volt, the diode will not start conducting. So how long does it take to reach 0.7 volt? So it is a 10 volt RMS. Can you tell me the equation for V in? How much sine omega? What is Vm? 10 root. Okay, you are trying to tell the answer. Just a second, let me just write quickly. 0 0.7. So yes, we have to this omega t is theta. We have been asked to find out omega t. So omega t is sine inverse of 0 0.7 by 10 root. Whatever it comes, it comes. But did you answer the? Do you understand the question or the solution? Very easy problem. It will stop also. Yep. Yep. You mean RL or only L? Okay. Only with L. That becomes a bit tricky. I will try to answer. Okay, let us not talk about diode non-linearity for the time being. Okay. We have only L, right? So, suppose you have the supply voltage here and the current. Looks like today we will uncover another concept also. Let us see how much we can go. So, this is the supply voltage. Thing is that we are just starting to analyze this circuit. We do not know what happened before. For the time being, we are assuming that the current was zero before t equals 0. If we are wrong in this assumption, we will rectify ourselves. Okay. So the voltage is this. Now we know that current, inductive current lags voltage, but those things we study in steady state only. In this case, it will start from zero. It will start from zero. So the current L di dt. So you see, when the diode is conducting, whatever the supply voltage is, the supply voltage is the inductor voltage, right? And inductor voltage is V equals L di dt. So if the inductor voltage is positive, the current through it will also become positive. Sorry, will be increasing. If the voltage is positive, the current through it will be increasing. So throughout this time, the current will keep increasing. Now, you see, this has become negative. This voltage has become now negative. So current will start falling. Why? Because L di dt is negative, so di dt is negative, so current is falling. What I feel is, yes, you will have a current like this. The diode will never turn off. The diode will never turn off. This is the current. Current will be throughout positive and the diode will never turn off. You can justify this in one way. Again, another concept. We will need it a lot while studying DC-DC converter. For now, just remember it. I will derive this later. At steady state, average voltage across an inductor is 0 over a time period. So you see, since the diode was diode was conducting throughout the time, the supply voltage was coming throughout the time across the inductor. So the inductor voltage is supply voltage, and we know that for supply voltage average is 0. So this equation is valid, means, so this is correct. Inductor will never turn off. Sorry, yeah, the diode will never turn off. The current will keep touching 0 and go like this. Looks like a half wave kind of sign, like this. Hmm. Okay, so now there is a small resistance. Now what we have is, we have source voltage is IR. Okay, so what will happen is, it will start conducting like this, but now we cannot say that this is equal to V. True. Hmm. Supply voltage, yes. VFR. So what we can say is that, see, current keeps increasing. I will draw once again. This is the supply voltage. And say, if I try to draw the current here, then say current is increasing and, wait a second, V is now less. One thing is for sure, that it will go up to like this and then come back, but this peak will now occur somewhere below this zero crossing. Somewhere below this, before this zero crossing. That is because this peak depends on L di dt, right? Now since you have one IR, your L di dt is supply voltage minus IR, and the current is already quite large here. and your supply voltage is dropping. So it has dropped quite a lot here. So this peak will happen somewhere here, not at the zero crossing. Okay. Now, when this current is reducing compared to the previous one, it will now reduce faster. It will now reduce faster because LDIdt is now not only Vs, which is itself a negative value, but also minus IR. So the DIdt is, the slope is much steeper. It will reduce faster than before. Like this. So you will have a small discontinuity here where the diode will be turned off. Larger the resistance, larger will be this discontinuity. Larger the resistance, larger the discontinuity. I'm sorry. Hmm. Yes. Hmm. Hmm. It is still negative. Hmm. Yes, in both the, say, beyond pi, if you are talking about, beyond pi, in both the cases, LDIT is negative. It has to be. But for the second case, the value is even more because of this current, IR. Acha, pi by 2. No, no, no. It cannot be. If the voltage across an inductor is positive, does not matter whether that voltage is increasing or decreasing. If the voltage is positive, current will keep increasing. Hmm. True. So the DIDT is positive, means current will be increasing. Yes. Yes. So RL load, RLE load, you will study. I don't know whether it is covered in this course, but we might study in rectifiers. There was some question in the comment box. Okay, last question for today. Any doubt here? What I discussed for this problem or after that? No? Okay. Alright, last question about thermal management of diodes. The admissible power dissipation of diode against ambient temperature plot is given below. What is the rated thermal resistance? Let us forget the question. Let us look at the graph first and ask one question to ourselves. That why at all with increment of temperature of diode, power dissipation power dissipation reduces. Should it be temperature of diode or ambient temperature? It should not be see, when they are saying temperature of diode, it means you had a diode kept in your lab and the lab say it has 30 degrees centigrade. So that is the temperature of the diode. Okay. They should have written ambient temperature. When you say temperature of a device, that is something else. The question anyway is correct. Power dissipation of diode against ambient temperature is given. Now, can you tell me, let us ask ourselves, why at all with increasing ambient temperature, power dissipation limit is reducing? Because if we can answer this question, then the question actually becomes very easy. See, the ambient temperature is something, say 30 degrees centigrade. Okay. And there is some current flowing through the diode that is creating some loss in the junction. You have some junction temperature, say 80 degrees centigrade. Okay. Now, between this 80 degrees centigrade and ambient 30 degrees centigrade, there is some thermal resistance. True. So whatever loss you have, whatever heat is being produced here, that will flow to the ambient and get dissipated. Now suppose this temperature is 80 degrees centigrade. Some heat was flowing. Ambient is 30. Now the ambient temperature say increases to 50 degrees centigrade for some reason. Never happens in India, at least most of the places. But say it now becomes 50. The thing is, previously when you had 80 degrees centigrade, you had a temperature difference of 50 degrees centigrade. And that was causing the heat dissipation in the environment. Now you have ambient of 50, so the temperature difference is now 30 degrees centigrade only. So the heat flow from the diode junction to the ambient is reducing with increasing ambient temperature. True. With reducing temperature difference, your heat flow will reduce. So if the ambient temperature is increasing, you have to reduce the power loss inside the diode. Otherwise, that much power cannot be dissipated and the diode will be damaged, thermally damaged. Okay. So if you see here, at 30 degrees centigrade ambient, you can have a maximum of 1 watt of power loss in the diode. Okay. But if you look at this far end, what it is saying, at 200 degree ambient temperature, you cannot have any power loss in the diode. What does it mean? It means that if your ambient is 200, you will have zero dissipation. That's why they are asking you to not have any power dissipation in the diode. Or in other words, at rated condition, the diode will have somewhere very close to 200 degrees centigrade temperature at its junction, which is unusually high. 200 degrees centigrade is too high. 150 itself is high. So from here, what we can understand is that the rated junction temperature is 200 degrees centigrade. Can you understand how I took this decision? Is it clear how I could arrive at this? Okay. If that is clear, then the next part actually becomes easy. Just a second, how to scroll this? So the rated is 200 degrees centigrade. Question is, what is the rated thermal resistance junction to ambient of the diode? So we can take any point on it and can find out the resistance because it is a linear curve, so it will not vary, the value will not vary. Let us take this point because we have already the data. 30 degrees centigrade, 1 watt. Just a minute, I'll take this one. So what we have is, this is just Ohm's law. We have V equals IR in Ohm's law. Potential difference is current times resistance. So temperature difference, ambient temperature minus junction temperature, is the current heat flow, which is nothing but the power loss times the thermal resistance, junction to ambient. So we have, sorry, it should be Tj minus Ta. Tj is more. So rated junction temperature is 200, ambient is 30. I have taken this point, you can take any other point, but then I have to see it with a scale pencil and then find out, say, what is this point. Here it is greatly given, so I am taking this point times R. So this comes out to be 170 degrees centigrade. Sometimes it is also called Kelvin per watt. 1 degree centigrade is not equal to 1 Kelvin, but delta T of 1 degree centigrade is equal to delta T of 1 Kelvin. So sometimes it, since we are talking about Tj minus Ta, it is also sometimes written as Kelvin per watt. Differences. Is this problem clear? Okay. Is there any doubt, or else I will terminate the session for today? Temperature difference will heat will decrease. It's like voltage. If voltage reduces, for the same impedance, current will reduce. Yeah. Mhm. Which part do you want to? I said I will explain something at the end. Can someone remind me what I said? I don't remember the very concept. This part I said I will derive in the DC-DC converter class. Maybe I don't remember what I said. Maybe I wanted to tell you that this omega t, if you do, it will come maybe somewhere near 2 degree or something, and that actually reduces the average current and hence the average voltage. Say if this was an ideal diode, maybe it would look like this, but this 2 degree, this value is so large, 2 plus 2 4, 2 here 2 here, because this voltage itself is less. We have at least 230 volt of grid voltage, at least in India, phase voltage. So in that case, if you use the same diode, this will reduce to very small amount, this degree. So at the end, the average will not be hampered much, which is negligible. That I remember, but what is? Can anyone else say exactly what I said? I don't remember also anything crucial here. I have sent in the chat box in case you joined later. I will. This is the link to my channel. Sorry. Oh, I've sent in the chat. I am sending his video link from where you can get to see his channel. But I think NPT will share with you everything, these notes and all. Last time also they did. Yeah. So next class again, maybe not maybe, but again next Monday, 6 p.m. once again. But what I am saying is, do not get much, you know, do not get much involved with the device physics and all. Be more conscious about the circuit operation, like the questions that Shanti was asking. These kind of things, these kind of difficult things, like what will happen if you change the loads and other things. Try to think more about. Yeah, go on. Hmm. Okay, let me draw the circuit first. So, you're talking something like this, talking about something like this. So initially, the current was flowing like this. As soon as I throw the switch here, no, the diode direction should be opposite. The current will start flowing like this. So if this is an ideal inductor and ideal diode, this current will keep flowing. So if I say at t equals t1, I threw the switch, the current through inductor will be like this. So when it was connected to the DC voltage source, it was increasing linearly because V equals L di dt. Then if I throw the switch at T1, it will become constant. It will never stop if you consider ideal inductor diode. And the voltage across the inductor will be zero. Why? Because di dt is zero. I is constant. No, not saturated. See, I turned on the switch. I threw the switch at T1. If I had thrown the switch at T2, it would look like this. It will keep increasing linearly up to here, then become constant. Saturation is not coming here. Again, if you consider ideal inductor and diode, then the voltage across the inductor will be zero. Yes. 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 The current is constant. You can think it this way also. The energy stored in an inductance is half Li squared. So if you have no component which can dissipate energy, there is no way this current will reduce. Yes. Sorry? Hmm. Diode, yes. Yes, forever. Yes. Yes. Only if everything is ideal. If you put a resistor, you can think it in two ways. See, simply think it like this. You have a resistor, current was flowing like this, there is a voltage drop like this. KVL has to be KVL must be valid. So if it is minus plus, it will be plus minus. You can think it this way, or you can think it this way. Since the current was flowing like this, you have an inductor, current will reduce. Current will try to reduce. But inductor will try to increase the current, Lenz's law. So plus minus. There are two ways to think. Polarity, it will be zero, inductor voltage will be zero. If you say in this case, if you have to draw inductor, say for the first case where I threw the switch at T1, if you have to draw inductor voltage, it will be like this, VDC then zero. And if you have a resistance, it will be VDC then negative, some negative. It will reduce then in that case because current will reduce. These things will get more and more, specifically inductors will get more and more uh, interesting when we study about DC-DC converters. Okay, then I will stop for today. Next Monday we will meet 6 p.m. Okay.